Hi! In this series, we'll be continuing the journey into ordinary differential equations, and previously we have seen how to solve ODEs using methods that gives us exact solutions to the ODEs. But we also recognize that most of the times these ODEs or IVPs, they do not have exact solution. And while we can use the theorem to tell us that there exists a solution, it might not be able to find them using analytical means. Therefore, we have to find it using different methods or approach the problem to understand it in different ways. One way is to use the direction field that we already know to sketch the behavior of the solution. And this gives us a qualitative idea on how the graph will essentially look like. However, direction fields themselves do not lead to any quantitative computations or comparison. It just gives you a rough idea of how it looks like, because these are just like the rate of change, so it must move from here to here and here to here and so on. So you can see how the direction fields provide a picture of how the y changes with respect to t. So how does the ODE looks like? But if you realize subtly, if you consider a point and then you start linking these tangent line segments together, you'll produce a piecewise linear graph that actually resembles the solution for the ODE. For example, if you look at this direction field, if you just link all the lines together, for example, maybe you get like this curve over here. While it's not an exact solution, it gives us a good approximation because it follows the same nature with the direction field. And so what it turns out is that this actually works, and it's been shown by Euler, and this method is known as the Euler method or the tangent line approximation. So you're given an IVP, and now we approximate the solution by using the tangent line as our guide. What does this mean? Okay, so you just look at this graph. The solution is originally this, and you know this is the initial point, but you know the tangent line value because you have the ODE, which is this function f, and then you just need to multiply by the interval that you want to change by, and that will lead us to the y, the direction change in y. Then you just add with the initial point to get here. So that's the y1. And when you're close enough, the t1 and the t0, then you become a better approximation. Because if you see here, now the distance between these two curves is this, but if your t1 is nearer, your distance shortens. Now we repeat the process and we just get t2, y2, y all the way to yn plus 1. And yn plus 1 is just the previous yn plus fn times tn plus 1 minus tn. So you can see how using this gives us a systematic way to approximate the solution for the ODE. And what's more is that now we get to see that if the solution maybe is this curve, our tangent line approximation will just be using from here. We see where the tangent line is by just summing to the ODE, then we go up, and we actually get a shape that resembles the solution. So let's take a look at an example. So for example, we have this initial value problem, and we just use the Euler's method to approximate the solution at t0.2 all the way to 1. And these are the following results. But we also can find the exact solution because we can use the integrating factor, and if you solve it out, you get to notice that the error within each answer increases in percentage. So that means, because like I showed you earlier with the graph, this is the original graph, the closer you are to the initial point, then the better your approximation, because the error is smaller. And if we actually look at this example in greater detail, we can actually see that if we actually decrease our step size, then it leads to a better approximation as well. So why is this the case? Is that, okay, so you look at this graph. This is the solution that we want. What we are doing is we are shooting from here, going to another solution curve, and shooting a tangent line from there, and going to another one, and continuing. So we are connecting successive solutions together to try to get an approximation. So if we use smaller steps, it becomes closer to the next point that we are shooting. So it reduces the error here. When you're shooting from here now, it will, because so you see from here, it like curves this way, then the next one curves this way, and so on. So the smaller your step, the closer the curve that you are shooting towards is resembling to the actual solution. Hence, that's why the approximation gets better. So you can look at these two examples to understand how does the approximation changes and the error changes with a smaller step size, or when you're closer to the interval initial value. And now we take a look at example 3, where we see that this is the Euler's method to approximate the solution, and this is the exact solution found. What we notice again is that it does tell us that the error increases as you go further away from the initial point, and what more is that the accuracy will also improve if your step size is reduced. But in this case, we actually realize one thing, is that the error becomes very, very huge already. So if you're just t equal to 4, you're like 50% wrong, or larger already. So in this case, we are starting to see that the Euler's method is not very effective in this aspect, and we can actually question why it's not that effective. And the reason for that is here. So we understand that we can use that when we solve a IVP exactly, we will get a infinite family of solutions. And what I already said is that what we are doing is we are shooting from one point to another point using a tangent line. Now we lie here, and here we'll have a new solution curve that is satisfied. From here, it will have a new tangent, and based on how the solution curve is shaped, it could shape something like this. So what happens is that here, the tangent goes here, but here the solution is like downwards already, so it goes down again. So the error here is so larger than the error here. So it's actually using a succession of tangent lines from different solutions some more. So not only are you using tangent lines, you're using tangent lines from different solutions. That's why if our solutions converge in a sense that it all goes in the same looking direction, then there's not really this problem to begin with, because all our solutions get closer to each other as t increases. But if you have a divergent family of solutions, this is where the problem comes in. So in this case now, because let's say I shoot from here to here, then when you extend it, it shoots all the way out here, and you can see like the error just keeps exponentially increasing. So this is when our Euler methods become a bad approximation, or a less effective one. Hence, for us to have a best approximation, a better and better approximation, we want to reduce our step size. We hope that our curves are converging. While we know that's not always the case, we hope so. But we can use the better step size, a smaller step size, and we just need to approximate T is nearer to T naught. So I hope you have understood how Euler method works and the general error analysis behind it. That's all for this video, and I'll see you again. Thank you for listening and have a good day. Bye.